Let me get started. So what I want to do in this final lecture is to wrap up with a few minutes of a few things that I didn't have time to say yet about the CMB. And then I will talk about non-Gaussianities, how to detect primordial non-Gaussianities and some interesting effects related to that. So let's start with the few things that I didn't say about the CMB. So in particular, I want to spend a few minutes talking about the CMB polarization again, which I quickly talked about at the end of the last lecture. So as I told you, this, and as you heard from Bill Jones, and you might have heard before, the CMB is partially polarized, linearly polarized, okay? And I told you that the source of linear polarization was the combination of scatterings, Thomson scatterings, plus the quadrupole, a quadrupole anisotropy. And this leads to linear polarization. So you should imagine that when you look at the sky in each direction on the sky, in addition to having a temperature for each point, you also have a polarization, which a polarization, linear polarization amplitude, or you need two numbers to describe it. You need, so what will happen is that if you point a polarizer in a particular direction and you rotate this polarizer, it will the intensity going through will not be exactly the same. It will depend on the orientation of the polarizer. And there will be a direction in which the intensity is maximum, okay? So imagine that, so at each point in the sky, there will be a degree of polarization. So light might be 10% polarized, 15% polarized. So and that just represents the difference between the intensity that you get if you put the polarizer like that and the polarizer at 90 degrees from that. But there will be, it's linear polarization. So there will be a direction in which you get the maximum intensity. So you would need to characterize polarization. You need two things. You need a direction and a magnitude, the degree of polarization, and the direction you need to put the polarizer to get the maximum intensity. And this, but this direction, so it's kind of having like a vector in each location on the sky, but it's not quite a vector because it's the same if you have the polarizer like that or you rotate it by 180 degrees, not 360, okay? So it's not a vector. It's not a field of arrows. It's a field of just rods in each location on the sky. But other than that, it's just very similar. So just so if you imagine making a map of the polarization on the sky, you will end up in each pixel a degree of polarization and an orientation. If it were a vector field, you will have all of these arrows in different directions. And in that case, you all know that if you take a region and you've measured all the polarization, you would be able to decompose this map into the vector field would be, you can have it to be a gradient of some potential plus the curl of some vector potential, however you want to call it. Okay, a gradient piece and a vector piece, okay, which you can isolate by taking the divergence, stuff like this, okay? So same thing is the case for a field of rods of the polarization of the CMB. In that case, you will split it into two pieces, which are usually called E and B. So E is the equivalent of the vector, the gradient part, and the curl part is B. It's called B, just names, okay? And it's pretty clear if you are going to, if you have, for example, let me just, for simplicity, draw to you a pattern of rods that is purely E and a pattern of rod that's purely B. So some pattern of rod around this point that is purely E would be something like that or something like that. Those would be purely E mode, a pattern that only has E modes. and a pattern that only has B modes, I should do this and rotate everything by 4. So it's some curly thing that I will screw up when I draw it. Let's see. So let's see, like this. So it's this. You know, this is one option. Okay, an example. These are examples, okay? And the other thing is same thing, but you know what I'm trying to draw, right? Like a curly thing like that, okay? So around this point, everything points radially. Around this point, everything tangentially. And if I rotate these things by 45 degrees in one direction or the other direction, I get one of these two, okay? So these are examples of B patterns. These are examples of E patterns, okay? Just example. The one thing that I'm making sure I say all the time is that if I give you a given polarization in one point, you cannot tell if it's E on B. It's a property of the pattern. Just like in that case, you at least need to take a derivative, a gradient, stuff like this to figure out what's the gradient and the curl part, okay? It's not a one location, it's B or E. It's about the pattern. It's a statement about the pattern, the symmetries of the pattern. In particular, the reflection symmetry and the parity of these patterns. If I put a mirror here and I reflect this pattern, it goes into itself. This pattern goes into itself. But if I make a mirror image of this one, it turns into this one, and this one turns into this one. Okay. So E is a scalar potential for the polarization, and B is a pseudo-scalar potential for the polarization. So I don't want to dwell on this, but the only thing to mention is that if I only have density perturbations in the universe, they will not produce any of these patterns. And by this I mean not that statistically on average there's nothing like this, but realization by realization, you should get 0 of this pattern. And it's not, in a case of scalar fluctuations, everything is the gradient of some potential, okay? So if you were talking about the curl part, if it's a gradient of some potential, it has 0 curl, so that's it. That's all I'm saying. So even if you had a single Fourier mode or many Fourier modes or what have you of density fluctuations, and you expanded the resulting map in any given realization into the gradient part and the curl part is identically 0. Any noise in your detector might create some, but you should get nothing of that. And that's why people want to measure the CMB polarization, to isolate this part, see if there's something there. And it turns out that if you have a background of gravitational waves, you do create this pattern. And so these people think will be the best way to look for a stochastic background of gravitational waves in the future. It's not the way current constraints on the background of the gravitational waves come about. Currently, so if I've already shown you the CL curve for density. So we've only discussed about these scalar fluctuations, zeta from inflation or from wherever they come. They lead to this. If I add a stochastic background of gravitational waves, the redshifts that these gravitational waves produce as the photons travel in the stochastic background of gravitational waves also generates temperature anisotropies. It will lead also to a power spectrum of fluctuations in the sky, which will look something like this. The amplitude here, I don't know. It depends on how much gravitational waves there are. But I'm not going to go into this because I want to move on. But the shape is something like this. You can calculate it. It's not very difficult. And so in the temperature of the microwave background so far, if there was a background of gravitational waves, the spectrum that we have actually seen is not just this one, but the sum of these two curves. These two curves, the gravitational potential, the gravitational wave parts have the following property. It produces significant fluctuations on large scales, but then they die off pretty quickly. So they don't affect all of the Doppler peaks very much. And so all of and these are the scales in which you have more L modes, remember, and this issue of cosmic variance that I discussed, that you only have 2L plus 1 at most, 2L plus 1 modes that you can measure in the entire sky, and that limits how well you can determine the power spectrum at any given L. Because the gravitational waves only contribute on large scales, they are easy to hide, because intrinsically this has large error bars, even if you measure like we have basically the temperature fluctuations on large scale with negligible noise. Even so, cosmic variance has sufficiently large errors that you can hide a contribution here without affecting the shape so much that you would have ruled it out, given the error bars that we have on those large scales. Okay? So the current constraints that you might see on the amplitude of gravitational waves coming from making sure that when we add these two curves, we don't screw up the shape here so much that we would have noticed. But this method is already done. It cannot do any better than it has, because the error bars on large scales will never become smaller than what they have, because they're just cosmic variance, and we don't think we can measure the temperature in some other Hubble volume for a moment. And so that's it. So that's where the current constraint comes from. In this EB decomposition, if you measure these B modes, there should be nothing there. So in some sense, the cosmic variance is 0, because it's not that you are trying to tell something from some big thing there, and you're trying to see that you don't add anything to it, but this has there should be nothing there. So in this channel, there's no cosmic variance, and so in principle, you can go lower than what we have. And so this signal is very small and difficult to get, as you heard from Bill Jones, but in principle, at least, that's the goal, to try to measure polarization as well as possible with sufficiently small systematics that you can decompose cleanly between a gradient part and a curl part, okay? And then in the curl component, see if you see anything, and if you see anything, it cannot be produced by density perturbations, okay? So I thought I should mention this at least. Yeah? So good, very good question. So vector perturbations produce also these. The reason density perturbations cannot produce them is that if you think of we're doing linear theory, so I can think of just one single Fourier mode. I have one Fourier mode. My problem has symmetry of rotation and parity around this mode. So the answer cannot break parity, okay? In the case of vector modes or tensor modes, you have the two polarizations, which you're treating independently, and you're considering one of the polarizations at a time, let's say the gravitational waves. And for a given one given polarization of gravitational waves does break this parity symmetry, so it will create more of one than the other. On average, there should be equal amounts, because there are equal amounts of gravitational waves of each of polarization on average, but you will still see some pattern like this. You could still produce it. Same thing happens with vectors. The only thing is that if you imagine that you put initial conditions. So by the way, maybe I should say, forget about inflation, forget about everything. If you just had to say, okay, I'm going to put some initial conditions, we've discovered that they have to be put in the very early on. Maybe it's some abracadabra. Abracadabra will create more or less the same amount of scalar, vector, tensor perturbations. Maybe they're all more or less the same. That might be an expectation. If that is your expectation, then maybe we should see gravitational waves, but we will not see tensor modes, because vector modes, sorry, because with the expansion of the universe, they decay just by angular momentum conservation. So if you put at the very beginning vector modes, they are so small by the time you get to recombination that there's nothing to be seen. Topological defect strings, for example, like you were hearing this morning, if that was the source of perturbations that now we've ruled out that is the dominant source of perturbations, but those that are generating things all the time generate more or less equal amount of scalar, vector, and tensor perturbations. So in a context of a defect model, the B modes that you see in the CMB polarization are not just coming from gravitational waves. They're also coming roughly equally from the vector modes, okay? And perhaps I should say one more thing, even though I'm, now that I remember, because about this, defect models. This fact that when you have the string network, you create more or less same amount of density fluctuations in density mode, vector modes, and tensor modes. Already, even before the peaks had been seen in the CMB, already was making these models not so good in the following sense. If I've seen 10 to the minus 5 in the CMB, and it's not all from density fluctuations, but it's like a third of it from density fluctuations, a third of it from the vector modes, a third of it from tensor fluctuations, then immediately the amplitude of the density fluctuations are smaller. And then if I measure the galaxy power spectrum and the amplitude of fluctuations in some other component, it didn't match. They were getting a very small sigma 8 for the people that are knowledgeable of this kind of terminology. So it was already not so good. You had to, I mean, there was once sigma 8 was more or less known, and it was already not something that there was already trouble in the air even before we see the Doppler peaks. Okay, so so this is about the ENB and stuff like this. I just wanted to mention this connection with cosmic variance and the reason of going to B, just trying to beat the cosmic variance that we have in the temperature anisotropies. And then let me talk about a few things in the late, a few effects in the late universe on the polarization. So I said that polarization comes from scattering and quadrupole. So one thing that happens in the universe, and I pretty much did not talk about it very much, except for the first lecture a little bit, mention it, is that the hydrogen in the universe eventually gets ionized again by the first stars, or maybe by the first. We definitely know that it gets ionized around redshift 10, and exactly who does it is it's what we're trying to figure out, but we definitely know that this happened around redshift 10 from the effect that I will mention to you now. So imagine that you have the last scattering surface. So before, and we're here hydrogen was ionized. Okay, there were this photon baryon fluid, etc. The universe becomes transparent. Photons began to travel. Eventually, at a redshift of 10, which in this conformal diagram, it actually covers a big region here. Hydrogen already, the hydrogen ionizes again. So there's free electrons here again. So these photons now can scatter again with the electrons here. But the density has dropped significantly because the density of electrons, because the redshift 1000 versus 10 is a factor of 100 cubes smaller density. So the actual optical depth, the probability that a photon will scatter from the CMB will scatter before reaching to us in some of the electrons that are here is only like 10% or so, okay, roughly speaking, okay? But for polarization, this has, especially for polarization on large angular scales, this has a important consequence, because imagine, and because the density is dropping, a lot of the scatterings happen earlier during this, so they happen closer to this edge than closer to us, okay? So imagine some electron here. Where are the photons that get to here coming from? They're coming from the last scattering surface of this guy at that time, which is this, okay? And so now, if you want the mean free path, so photons are able to travel all of this distance, and this electron now sees a rather large quadrupole from the differences in the density here, here, here. And so the scattering of those anisotropies leads to some polarization, which on large angular scales dominates. It dominates because a large wavelength mode, let's say if I consider a mode like this large, compared to the mean free path that would subtend on the sky a big angle for us as you go from the maximum to the minimum, compared to the mean free path at recombination, which is something very small, this mode it's barely it barely changes over this mean-free path. So it cannot generate any polarization because the photons do not travel significantly to see that there's any difference between the last two scatterings. But now between recombination and reionization, the photons travel significantly larger, and so they can start exploring this larger wavelength mode and seeing that there's some difference. And so there is some polarization on large angular scales produced by these scatterings. And so if you were to plot the CLs for the polarization in a log-log way, so they look something like this without the reionization, but because of reionization, there's a big bump that dominates over what would be there, even though there's only 10%. Even though only 10% of the photons scatter, the polarization of large angular scales is dominated by those scatterings, okay? And so this is a significantly big effect. This has been seen, especially in the cross-correlation between temperature and polarization by WMAP. And this is how this 10% figure was determined, by seeing the height of this peak. Basically, the more scatterings there are, the bigger the curve, or okay, the bigger the bump. So that's how we know exactly when the hydrogen in the universe was ionized. And it has, for people looking for gravitational waves, as you heard from Bill, in the B modes, also it creates the same bump for the same reason, and so it enhances the large-scale polarization signal in such a way that it will make it, at least if you're looking for it on the large angular scales, it makes it easier to detect. Okay. So that's the effect of reionization. And the other effect that I wanted to mention is that of gravitational lensing, which was also mentioned by Bill. So I told you E and B modes, density fluctuations cannot produce B modes. That is only true in linear theory, in which I'm considering one mode at a time. But once I have some nonlinear effect, that's no longer the case. In particular, gravitational lensing is one of such examples. What happens is the following. When we think we're looking in some direction, we're actually not, in the sense that the photons, if we trace it back, they are, they come from slightly different angles than the one we think it's coming because of the deflection of light by the intervening large-scale structure. So if you imagine having a map that is perfectly E-mode polarization around some spot, and now you take this map and you randomly move, because of lensing, the location of this, you deform the shape of the map by moving these rods randomly because of the random deflections, okay? You will end with a map that's no longer just E. It will have a little bit of B. And a simple example that you might do to convince yourself of such a thing is if you imagine you start with a vector that is just the gradient of some potential, okay? And now imagine that you will shift this vector by a random thing. So you will go from x to x plus some shift, which is what gravitational lensing would do. That depends on x, okay? So now what you actually observe is not the gradient, but it's like the gradient of phi at this shifted location, okay? Imagine this is what was happening, which is pretty much what is happening in this case. You can easily convince yourself that this thing no longer is a perfect gradient, okay, in general, okay? Of course, if this is just in some cases it is, but if you just put a random function here, this is not a perfect gradient anymore. So you generated a curl for the observed thing, even from something that didn't have any curl to start with. And so that means that even if you only have E, you will generate a little bit of B. And that is one source of contamination for these searches for B modes. Yeah?
So from the, it is
Uh-huh. And by that peak, you mean so in my simple explanation, I just assumed that at some point in time, the universe reionized. But what if this was a more complicated thing? Reionized, it recombined, it did something, it went there, come back, and reionized again. All of this at some level would be encoded in the details of this shape of the power spectrum of the E modes and the bump, this extra bump. But only at some level. So it turns out that if you start, there's a big cosmic variance there just because it's at low L. So even if you measure polarization perfectly, you won't be able to determine an arbitrary, strange history of ionizations and recombinations. You can basically just get a few numbers out of the shape of this peak, which are the total optical depth, or the total probability that a photon scattered. The next number is more or less at what redshift this happened, or something like if you start moving like 2 peaks or something like that, you will maybe start affecting. And then that's about it. You don't have enough statistical power to get a crazy shape there. And also it's difficult to arrange such a crazy shape because at the end of the day, what's happening there is that the first stars are turning on, or whatever they are, and ionizing the universe. Of course, this will happen, for example, over a Hubble time. It's not that everything is perfectly synchronized. Furthermore, if you turn off these stars immediately, which will not happen synchronized everywhere either, it takes some time for the hydrogen to recombine. So it's never going to be like a crazy thing that is suddenly going up and down and up and down. But you can imagine, and during some time I should say that trying to play with strange histories there was fashionable, because WMAP during I think it was the first year release, or maybe it was the third year, I'm forgetting which one of those, saw a number which was pretty high for this optical depth, something that made people think that maybe there was some very early epoch of reionization, because if you reionize the universe earlier, because the density is higher, you get it's easier to get a higher probability of scattering. And so I don't remember what was the number, it's like 17%, I forgot, it's just so many years ago. And then it went away. And so people were playing with putting little peaks in the past and stuff, and seeing how they could engineer these by the first generation of stars turning on, ionizing the universe, but also heating it up, preventing future stars from forming for a while. And so you had a period of recombining in the universe, and then again new stars form, and so on. So there was some playing around, and it's not impossible. So people at the time constructed situations in which a couple of features could be put into this reionization history. But now it looks less necessary, at least, to do it, to play with that. Okay, so just the last words about then the CMB before I move on to these non-Gaussianities I want to spend a little bit of time talking about. So then I said that we can fit all of these observations with 6 parameters. So I want to spend like a couple of minutes just reviewing then exactly what these parameters were and where we are getting them from the CMB. Okay, there was an amplitude and an S, and there was this optical depth of reionization. So I think I now told you about all of them. So these were the 6 parameters. We are getting these from these 2 are what determine the physics at recombination. So where matter radiation equality happens relative to the epoch of recombination is this thing. the weight of this photon baryon fluid is this thing. So it sets, for example, the relative height between odd and even peaks. And in fact, because we have also now measured the damping scale, it's an over-constrained thing. So even though we have 2 parameters, we've measured more things than 2. And so things work out, but you could even add another, you could add like a number of neutrinos or something. You can even measure one more number, or there has been a consistency check that this has worked, okay, at recombination. Then you have to translate these scales of the horizon at recombination and so on into an angle in the sky, and that is where the distance to the last scattering surface comes in, and this, for example, has to do with omega mater and omega lambda, okay, for example. And this is where we can get some constraint on some late-time parameters like this. The optical depth of reionization, I've just told you how it's determined using the CMB polarization, okay? So this is from where this comes from. And this, well, the amplitude of fluctuation is just the overall amplitude of delta t over t in the CMB. And this ns is just a tilt of the initial fluctuations that if we think we understand this, what the transfer function was, what I called yesterday, the transfer function is doing, you can tell whether there is some more fluctuations on large scales or small scales. And we seem to have seen more fluctuations on large scales. So in the initial conditions. So you need to put a little bit more fluctuations on large scales than small scales in order to fit the data. So this is where everything is coming from. And just a final note on this. Just to point out the basic CMB degeneracy that I think I pointed out at the beginning. So if you have omega lambda, I showed you, I gave you a plot in this handout at some point, an omega mater, and this is a flat universe, okay? They both summing to 1. So if you allow, so as you change omega mater and omega lambda, you change the distance to the last scattering surface, okay? So you would change for a fixed physical distance of the horizon at the time and so on, you would change the angle it subtends. Because we've measured the angle of the peaks, we already know this distance to the last scattering surface in some sense. So if you want to keep the distance to the last scattering surface fixed, you can do it moving in this plane of 2 parameters. There's a line here in which the distance to the last scattering surface remains fixed, okay? But as you move in this line and you increase omega mater, not to screw up the physics of the peaks, you need to keep omega mater and the shapes and so on, you need to keep omega mater and omega baryon h squared fixed, okay? So as you increase omega mater, you need to reduce the Hubble constant in order to keep omega mater times h squared fixed, okay? And you need to increase omega baryon in the same proportion as you increased omega mater so that you keep omega baryon square fixed as you change the Hubble constant. But you can do it. You can see I can move here, adjust omega mater, adjust the Hubble constant to get this parameter the same, adjust omega baryon to get this parameter the same, and I will get a more or less equally good fit to the CMB data, okay? And this is true except for some ISW effects that I have not discussed very much on large scales and things like that. But for the most part, this means that when you fit the WMAP data, there's a degeneracy. This is a well-known CMB degeneracy that a lot of models with different parameters fit the data reasonably well. And so now you have many options, but you're changing the Hubble constant. So by the time you're here, you're in a Hubble constant of 30 kilometers per second per megaparsec, or 40, while we know from direct measurements that it's more like 70, okay? So now it's very easy. You need to combine the CMB with something else. For example, a direct measure of the Hubble constant will tell you that you're here, okay, which happens to coincide with the line of flat universe. So, or if you assume you're in a flat universe, you already know that you're here and you can figure out the Hubble constant. Or you can combine it with some other measurement. And we usually very well determine that we are in this location, okay? But I just wanted to go through what the parameters were and the fact that this degeneracy is there. And so unless you assume a flat universe, which is probably a reasonable starting point, you need to use something else. But by the time you are significantly far away from a flat universe, this is it doesn't have a big angle with respect to the flat universe line. So by the time you are significantly away from here, you have ridiculously low Hubble constant compared to just the direct observations. Okay, so it's very difficult to not be very, very close to the flat universe. Okay, that's why at zeroth approximation, when Boomerang saw the locations of the peak, everybody said the universe is flat. Okay, because this line is, even if you move the Hubble constant, if you just really move it over some reasonable range, you're just so close. You're on top of the flat universe. Okay, any questions about this? No? Okay, let me talk a little bit about non-Gaussianities then. So Paolo spent quite a bit of time calculating 3-point functions from interactions of the inflaton during inflation. So I thought I would spend at least a little bit of time talking about how we go about trying to see if that is there. Of course, we don't need it at the moment. So we only have upper limits. And if you should take anything from these lectures, is that the simplest of, I mean, with these 6 parameters, we feed everything, and we don't need anything else. Non-Gaussianities, isocurvature, whatever you like, you don't need it at the moment. Maybe, hopefully, Planck will change this situation, but maybe not. I don't know. At the moment, we don't need anything that is not the simplest thing you can possibly imagine, except perhaps that it may have been simpler to just have Harrison-Seldovich spectrum, ns equals to 1, and we don't see it. Okay, so what about if you, how would you go about trying to figure out if there were some departures from Gaussianity in the CMB data, for example, or in large-scale structure data? The easiest thing to do would be, and by Gaussianity, in this context, we would just mean, for example, I go to the CMB WMAP maps, and I do a histogram of the number of pixels as a function of their temperature, okay? I just plot it. And this should be a Gaussian. And it's a beautiful Gaussian. You should really go and look at one of these WMAP. I don't remember if it's in the 7-year papers, they still have these things, but in one of the previous incarnations, for sure, there are the histograms. And it's a Gaussian to to many sigmas in the tail, okay? So if you want, the CLs are just, or it's just related to the variance of this distribution, okay? And then you can ask the question, is there any kind of departure from Gaussianity? So for example, you could try to estimate so let's call you can try to see if there's a non-zero value for t cubed by just summing the t of all the pixels divided by the number of the pixels, by doing that and seeing if you see something that's different from 0, okay? Of course, you will see something different from 0, but the question is, if you see something different from 0, which is larger than what you just expect because of the random nature of this thing, right? Even if I give you, I don't know, 3 samples of something that is a Gaussian distribution, if you cube them and sum them, you will get something. You will not magically cancel, just the average that has to cancel. In fact, the average, you're trying to see if this is 0 or the typical size of the spread that you will get if you do this. So if you wanted to measure this, you would do something like that, and the question is, do you get 0 or not? And the typical error bar that you will get has something to do with sigma cube over the square root of the number of observations, okay? And there's some numerical factor like 6 on the top, okay? So if you have 1,000,000 pixels, you can figure out this thing to a part in 1,000, okay? You can check whether there is some departure from Gaussianity of a part in 1,000. And this is what has happened with WMAP. Okay? We've gone, checked, do something like this, and million pixels apart in 1,000. And we haven't seen anything pretty much. Okay? In reality, what is done is slightly more, and you could do, before you could do something even, you could do look at more, you could do look at t to the fourth. Do you see anything anything in t to the fourth? Of course, in a Gaussian you will get something for t to the fourth. So just the part in excess of you that you would get in a Gaussian, which is usually called the connected part. So do you see something here? And again, the typical value that you will get is given by sigma to the, in a Gaussian random field will also be like this, with some other coefficient here, bigger than 6, 4 times 3, etc. Okay, so you could do this with arbitrary endpoint functions if you want. But the type of error is always, especially if you don't go so far that this has grown a lot, it's always like square root of n. Okay, the number of pixels is. I mean, if you have a histogram like that, it's easy for you to do this calculation. And so so what has been done is slightly more sophisticated than this, in the sense that as you saw in Paolo's lectures, we have some expectation as to so we measure the CMB not in it's a map, a two-dimensional map, or we measure large-scale structure in a three-dimensional volume. So we have all of these different Fourier modes that we have measured, and what we really can calculate is some sort of three-point function in Fourier space, okay? And this should be, by translation invariance, some delta function and something called bispectrum, in this case, K1, K2, K3. And there are various shapes for this, depending on which are the interactions that created this. So non-Gaussianities, as you learned from Paolo, come from interactions of these fluctuations in the inflaton field, for example, in the case of inflation. So depending on the particular shape or on the particular reason for those interactions, you will get a different form for this B, which then, because of the translation invariance, is just a function, is non-zero for 3 k's that add up to 0, but it has a non-trivial dependence on the shape of this triangle. It overall goes as k to the minus 6 by scale invariance if you just make it the whole triangle smaller or bigger, but it can have nice dependencies on the shape of this triangle, whether it's a kind of an equilateral triangle or a squeezed triangle or what have you, okay? So what you would want to do is not just take the histogram, but somehow measure the temperature in Fourier space or in L modes is the same. Take this kind of 3 products of the temperature and try to see if you can detect a specific shape and differentiate between one shape or the next, okay? And so this has been done. So what has been done is to, rather than just summing the temperature at each point in the sky, what you do is you sum the temperature, the ALMs of the temperatures, 3 ALMs of the temperature, ALM 1, ALM 2, ALM 3, okay? There's an equivalent thing to the delta function, some 3J symbols and stuff like this. Let me not go into that. So only there's some relation between the L's and M's that you need to include in this sum that's dictated to you by symmetries. But then what people do is basically invent some sort of weight here as to how to combine the different triangles, the different triplets of ALMs, sum them all together to get some kind of constraint on what this I'm writing would be the equivalent of summing t cubed. In this case, I'm summing all of the possible ALM pairs, triplets, and I invent a W which tries to pick out individual shapes, right? So it's kind of a filter, if you want, that is similar to the, if it were in 3 dimensions, if you have something that peaks in this configuration, you would sum these guys as opposed to these other guys. And so you would just try to sum up all of the triplets with a weight that preferentiates the ones that are supposed to have the signal given your expectation for a particular model, okay? And because there's just a few of these shapes that seem to come out from these calculations, one that's called an equilateral type shape, the squeeze shape, and one usually called orthogonal shape. So there's like a few of these ways that you need to consider. People have done this, find what is the best weight that you should use in order to try to detect the non-Gaussianity of a particular kind, done this sum, and compare this with what you might have, what you just get from noise, Gaussian noise, which is the equivalent of sigma cube over the square root of number of pixels, okay? And in none of these situations have they seen anything that is strange from the point of view of a Gaussian random field. So that's, I will not quote the specific constraints, but maybe Paolo did it, I don't remember. But the one thing that I do want to emphasize is that the kind of constraints on the level of non-Gaussianity that you get are still of the, if you do this with triplets and in Fourier space and so on, the error bar on the level of non-Gaussianity is still of the size 1 of the square root of the number of pixels, okay? And I leave you for the ones interested to do this as an exercise. And by this I mean that if you start thinking about, in the case of the histogram, you have n pixels and the sum involves just n things, and so it's reasonable you get just square root of n. You might get confused in this case because if you start computing the number of triangles that you can possibly get, it grows much faster than the number of pixels cubed because there's n number of pixels for each of the Fourier modes. And now I have 3. Okay, I only have 2 because one is set by the fact that you have to add up to 0, but it looks like I have a lot of possibilities. So these sums are not going over n pixel things. They're going to more like n pixel square things. But in the end, but this is what you get in any case. So, and that's why constraints are all on the size of 10 to minus 3 for these non-Gaussianities. Okay. And so one, so let me make a few. Any questions about this? Yeah.
Just considering the non-Gaussianity is introduced by, I don't know, linear evolution.
Yes.
What is the expected size?
The expected size of that is 10 to the minus 5. In the same units that I'm telling you that we've detected 10 to the minus 3, it will be 10 to the minus 5. It's because it's the effects that we are sure are going to be there are effects of the order delta rho over rho squared, and that's 10 to minus 5 down from. So that's the level. Although I should be a little bit careful in the following sense. There are some effects that are not happening at recombination, but along the way, that are much bigger. For example, gravitational lensing, and this has already been detected. It only produces a 4-point function in the temperature, and this has been detected by the ACT experiment for the first time, I must say. So there are non-Gaussianities that are bigger, or some more astrophysical origin that along the line of sight, things that happen along the line of sight. But if the question is how non-Gaussian are things if you were an observer there at recombination and measuring something, that would be 10 to minus, the equivalent of 10 to minus 5 in the same units that I'm saying that we've now constrained 10 to the minus 3. And this is the FNL times zeta kind of thing that Paolo was saying, okay? So for whatever the reason, people normalize this thing using these FNLs, and so the actual level of non-Gaussianity is this FNL times 10 to the minus 5. This is not even, I mean, times some numerical coefficient here that can be even a factor of 10 that depends on the details of the shape because they're actually normalized. The FNL is defined in the equilateral by the amplitude in the equilateral configuration, but the things like the squeezed triangles have much more amplitude on some other configuration, and so even if you normalize two of these shapes in the equilateral, they really mean different levels of non-Gaussianity. So there's, unfortunately, it's a little bit of a confusing way of naming things, but that's what. So these things that are there just from the nonlinear evolution corresponds to an FNL of order 1. And this is the level of the actual non-Gaussianity, which would be defined, for example, in the case of the dimensionless thing, right? T squared to the 3/2, okay? So this would be what people would call the skewness of the distribution. This would be of the order of FNL times zeta. So this is 100, this is 10 to the minus 5, this is the 10 to the minus 3 level that I've been talking about, okay? And when you put here 1, this is the size of the corrections that you might expect just from the nonlinear evolution at the time of recombination. Okay. Yeah. Yeah, this is a very good question. Because of the level of statistical, because of the size of the error bars that current experiments have, this has not become an issue at the moment because we can only, especially for the 3-point function, we can only see FNLs of order 100 and the nonlinear evolution at recombination and things even that happen along the line of sight in the 3-point function are pretty small. So they are smaller than our current error bars, so we haven't worried about them. At 0th order, that's what the answer would be. Even for Planck, it's kind of marginal whether things happening at recombination are important or not. But if we had better error bars, we would definitely need to figure it out. Now, the shapes are not the same because, well, clearly, these effects from nonlinearities are not scale invariant because the density contrast is larger on small scales than on large scales. So if any of these effects, astrophysical effects, are not scale invariant. So that's one way of disentangling it. Sometimes, if this is produced by some other kind of some non-gravitational astrophysical thing, it will usually lead to a frequency dependence of the effect, like the Sunyaev-Seldovich effect. So we will be able to tell apart that. But there will be some, there definitely might be some lower level of non-Gaussianity that we can probe with any specific measurement type, given for once the astrophysical and non-complications are sufficiently large, we will not be able to disentangle everything, okay? But we are not at this level now. Any other questions? No? Okay, so two other things that I would mention about this, or one thing that I want to mention about this searching for non-Gaussianities. There's another line of attack to this, which is looking for odd things in the map. And odd things in the map, there's been many claims, like the cold spot and many alignment of the low L's, et cetera, et cetera, et cetera. The Stephen Hawking initials in the temperature map, if you look at the CMB map, there's an S and an H. So there's a lot of peculiarities in the map. And then, it gets very tricky very fast, okay? So looking in the way that things were presented by Paolo, and I'm talking about here, there's some expectation of something. I go look for it, okay, and I see it or I don't see it. I can figure out a priori how, what range of things I might expect for some statistic in a Gaussian random field. I go do it in the data and see if I see something that is, but I'm looking for a specific thing. The other situations are more a posteriori. I look at the map and I see something strange, like an S and an H, and then I decide to invent statistics that would pick up the S and an H, and then I run a lot of Monte Carlos to try to figure out when would I see an S and an H, or how many times would I see a letter in this font. I don't know. So it gets tricky because you've already seen the strange thing, and then you're inventing the statistic, and then you're running the Monte Carlos. But in some other map, you will pick up something, the complaint is that in some other map, you will pick up something different that is odd, and you will invent the statistic for this. So it's a posteriori thing, and then you will always find something odd in a sufficiently large thing. You will always find something odd by eye, and then if you start inventing a statistic that picks that up, and then running Monte Carlos of a Gaussian random field, you will get something that is more significant than if, because you already started with a weird thing, because that's why you're doing the whole exercise, okay? Now, of course, if the chances that you would see something odd is so minuscule, then eventually you will get convinced anyway. But for the most part, these anomalies are, borderline strange, even after you've done all of these a posteriori things. So most people just go about their lives ignoring them, and that's it. For the moment, at least. But who knows? Maybe. I've never seen somebody trying to actually quantify the Stephen Hawking, how unlikely that is. Should you take into account that Stephen Hawking is actually Stephen Hawking? Or what? Yeah, well, 2 letters. Okay. But Stephen Hawking is a physicist, right? So I don't know, anyhow. Should you take this into, and it's not any physicist, of course, anyway. That would be more clear, exactly. Okay, so good. So I'll start looking, maybe if I project them up in a different way, In fact, I was looking at this ball that Paul, I was trying to find the S and the H, and I couldn't find it in the ball. I don't know. So it might also be the way we plot the. So anyhow, if somebody finds the S and the H in the form of the ball, just show it to me, because I couldn't. I spent like some time trying to find it, and I couldn't find. I don't know. Yeah. Anyhow, let's just stop there. Okay. So the last thing I want to talk about is a way of looking at some of these non-Gaussianities in the context of large-scale structures through a method that's called a scale-dependent bias. And the reason, I want to talk about it is because I think, first of all, for some specific type of non-Gaussianity, it is competitive with the CMB at the moment, and it seems that it will be much better than the CMB if you just make optimistic projections, but on both sides. So if you make optimistic projections on both sides, it will win. And it also is sensitive to cases of non-Gaussianities, which are, I think, for me, quite interesting, which are the squeezed limits. So imagine having correlations between the very long wavelength and a very long wavelength or short k and a very long k. And this is something that single field inflation cannot produce, as you learned from Paolo, because of some very clear arguments. Just this mode crossed the horizon much before the other one, so it was totally unobservable for anybody that was living there during inflation. In particular, the small-scale modes could not figure out that this long mode was there, and so their amplitude cannot depend at all on what this guy, whether this one has fluctuated up or down or what have you. So it's very clear that in this limit, the 3-point function vanishes in the case of inflation. single field inflation. And if you start mucking around and putting other fields, you always generate something which is reasonably big in this limit. And this is the limit this scale-dependent bias works. So let me tell you about what the observable is. And I'll spend some time because I find it's quite interesting, and you naively might worry, but I think it's it's really a very good idea. So what the thing is, so you already heard from David, if you plot the matter power spectrum in lambda CDM, it has a shape like this. However, when we go out and try to measure the power spectrum, the clustering of matter, we don't go out and measure the location of dark matter particles, but we try to trace this structure by measuring the location, say of galaxies. Okay? So this is just the two-point function of dark matter in Fourier space, so two-point function. What about if I did the same thing with galaxies? So of course there'll be a scale here, given by the nonlinear scale, or a complications due to galaxy formation, in which I will not trust anything that I get with galaxies. But if I go at sufficiently large scales, the claim is that you would see the exact same power spectrum, maybe multiplied by some unknown factor, depending on on the properties of the galaxies that you're looking at, called the bias. So the whole thing will be shifted up by this factor of the bias, up or down. Okay? So, and I think some of you have as an exercise to calculate this bias using Preshekter. David gave you this exercise. So the claim is, okay, so if you went out and measured galaxy power spectrum, and people have, they see a shape that is the same as the matter, or the one predicted by lambda CDM, except for an overall bias. If you look at galaxies of different type, this bias changes, and so on. And so, okay, so the claim is that if you had a universe in which the initial conditions had non-Gaussianities of this type, so a large three-point function of this type that is non-zero in the limit of very squeezed configuration, so large modes, long wavelength mode, long wavelength mode changing the short wavelength mode, you would see a scale dependence of the bias. So when you go to sufficiently large scales, rather than this just being a constant, it will be something that even this ratio grows with, as you go to lower and lower k, this separation becomes larger and larger as 1 over k squared. Okay? That's the claim. So first of all, the presence of this non-Gaussianity is encoded in a two-point function. That's maybe somewhat surprising, but also it's a good thing, because measuring a two-point function is easier than measuring a three-point function. But it's encoded in this ratio, in this bias that looks like an astrophysical thing, and it's nothing that we can compute on first principles. So you might worry, okay, whatever, I have no idea about this, and so if I were to measure a bias like that, well, maybe there's some complicated something going on in the galaxy formation, I don't know. I would never be able to trust this. But this is not the case. I think you can trust this very much. And so I want to spend a little bit of time telling you where this comes from, okay? And where this k squared comes from, because it's pretty easy to figure out. And because of that, you will appreciate that you can trust this very much. Okay, so let's take the following situation. Okay, so imagine, so let's draw, so this is space-time, this is us, okay? These are the surfaces of constant time, something or other in our space-time. And what we are doing then is looking at back to some little region here, okay? This is our survey of galaxies at some particular redshift somewhere there. So we are making a map, and as we observe a bunch of galaxies with a given redshift and a given angle on the sky, theta and phi, we count galaxies in little volumes of redshifts, theta and phi. This is what we're doing. And they're all coming from some little region. For simplicity, let me do that. So this region is filled with little galaxies that we are counting and making a map of the galaxies inside this region. Okay? So now the question that I want to ask is, so first point is that in order for assembling these galaxies, matter has moved around. By what kind of distance has it moved around? By what's called the nonlinear scale, something around 8 megaparsecs or 10 megaparsecs or something like this. So on scales of this size, matter has rearranged itself in order to form all the objects that we see in the universe. Okay? But so now, this effect of the scale-dependent bias is kicking in on much, much larger scales than that. So we are asking the following question. Imagine there was some long wavelength modes in this universe. Okay, so there's these long wavelength modes. And this is our little region of this box here. Okay? And we're asking the question is, because of the presence of this very long wavelength mode, and I'm trying to ask the question, in this region of the survey, how many galaxies formed, okay? This mode that I'm looking at is much larger than this little region, but this little region is still much bigger than this 10 megaparsecs. So it's a representative region of the universe. There's several galaxies there. I'm just trying to figure out what the fact that there is a very long wavelength mode, how does it affect the number of galaxies that end up forming in this region, okay? And then I'll ask the same question but over here and so on, okay? So you have to ask the question, if you're sitting here and you're an observer there, one of these galaxies, or you have your world line following the matter there, what kind of universe do you see in the presence of this long wavelength mode, okay? And it should not surprise you that what you see, if you are sitting there, especially, let's take this to be a spherically symmetric configuration, because given that I'm trying to calculate just the two-point function, that's enough, really, for me. Because the thing that I'm going to calculate is spherically symmetric. So, it should not surprise you that if you're here, the space-time around you is exactly that of a curved universe, identical to a curved universe, okay? With a curvature, the curvature scale is just given by the Laplacian of zeta. And to be more precise, some 2/3 or something, minus 2/3 of that. So if you are in this region, the long wavelength mode, all that it has done to you is that you think that you live in an FRW which is slightly curved, very small, okay, with a curvature given by the Laplacian of zeta, okay? So if you're interested in understanding how many galaxies you would form there, you could imagine doing something else. If you have a computer and you run first principle calculation of galaxy formation, and somebody tells you, I now know how to calculate as a function of the proper time in a universe without a long wavelength mode, just in a homogeneous universe, the number of galaxies that you would form at a given proper time in a universe with a particular value of the curvature given by this, okay, with some initial amplitude of the perturbation. So you could imagine doing that and calculating in the computer or using projector or however you want the number density of galaxies in a curved universe as a function of the time in this universe, and given some initial amplitude of fluctuations on the small scales that will lead to the galaxies, okay? So what I'm trying to convince you of is that if you're sitting over there, okay, the only effect of the long wavelength mode is to make the universe slightly curved for you. And so the number density that you would observe here is just the number density that you would observe in a flat universe plus the derivative with respect to omega curvature times this Laplacian of zeta, okay? So the local number density that an observer would see here is that of a curved universe at that particular proper time of this observer. Okay? So in other words, this, and of course this is the case, no? Zeta is a gravitational potential, so the only physical thing is really the curvature, the Laplacian of the potential. So if you're an observer over there, the only thing that this gravity, that the fact that the universe is inhomogeneous will lead to is tidal forces, which is what this is. And so the only physical effect is proportional to this to the tides, to the Laplacian of zeta, okay, or the Laplacian of the gravitational potential. Okay, so the number density in this region is just given by then the number density in the flat universe, okay, at that proper time plus the derivative of it. If you imagine these are functions that you know from your computer, your projector, or whatever you want, okay? Times the delta omega, which is Laplacian of zeta, plus blah, blah, blah. So, and we are sticking to first order, so it's just this. The changes, okay? They're just Laplacian of zeta, okay? Yeah?
Why do you have spherical symmetry in the small?
No, just because in that case is exactly a curved FRW.
But the mode flows in one direction, right?
Sorry?
The long wave mode picks up.
Yeah. So that's why I said, okay, let's consider a situation in which it's not a Fourier mode, but just an overdensity spherical around this point. Because in the end, I'm going to calculate the two-point function of the number of galaxies here versus not, and then averaging over direction. You can convince yourself that the fact that this is a Fourier mode, this anisotropy, it cancels out. So for the purpose of this talk, let me just take this to be a spherically symmetric thing. So then it's clear, it should be very clear that this should be like a curved universe around that point, okay? But the argument goes through even if it's not, if it's just a single Fourier mode, it's slightly anisotropic universe. But the point that all that matters is the Laplacian of zeta, the Laplacian of the gravitational potential, which is proportional to the delta, the density fluctuations. That should be clear, okay, from the equivalence principle or what have you, yeah? Yes, thank you. That's what I meant. Yeah. Yeah.
I'm a little confused by this because usually the number density is given by the peaks of some initial.
Yeah. So
But why should this fixed value density affect the number of peaks?
yes, because so in the standard way of saying it, you have the peaks on top of some long wavelength mode, okay? And then you have a threshold, and galaxies form this is a simple model. Galaxies form when you cross 1. And so the fact that there is this long wavelength over density makes it easier for you to cross 1 here than there, okay? And the effect of this long wavelength mode is to make more galaxies here than there with this bias. But it's nothing, I mean, this bias is nothing other than the derivative of the number density of galaxies with respect to omega. Because this is also a universe with a different omega, okay? So it's the same. I'm just telling it to you this way because if you follow this argument in detail in ways that I will not have time to do today, you can also figure out all of the GR type effects. This is not something, I'm not using, in this way of writing things, I'm not using Newtonian approximation or anything like that. Or I don't even have to tell you what is the process of galaxy formation. I'm not having to tell you anything about the details of anything, really, about how this comes about, okay? Cooling, this, that, or the other. It's just the space-time around this point in this limit is identical to a curved universe. So if you know how to calculate the abundance of galaxies in a curved universe as a function of the curvature, I don't care what your process is. The derivative of this with respect to the curvature gives you what the local observer will see, okay? That's why this is slightly more, I don't know. That's the, okay, so if you're a local observer there, you will see, and you count galaxies. So imagine that now we think of the fact that there's like some local observer here measuring galaxies, some observer somewhere else measuring galaxies, tells us a signal. It says my proper time is this. I've measured this number of galaxies. Okay, so the only effect that you will see happening is this dependence on the long wavelength mode is through this Laplacian. The only thing that can be there. Okay. So what happens if you have a universe with a big 3-point function of this kind? A 3-point function of this kind, what it physically means is that if you take two Fourier modes and you multiply them together, that's the power spectrum, right? It's the k and minus k, the average of k minus k. This 3-point function is nothing other than how the power spectrum changes with space correlated with the long wavelength mode. Okay? So another way of defining this is to measure in the different regions of the universe the power spectrum, okay? Just making the k's add up to 0 in these regions, then Fourier transforming the amplitude that you measure in these little regions with the long wavelength mode, that is identical to doing this. So it's two ways. So a universe with a lot of non-Gaussianities like this is a universe in which the small scale power varies from place to place, correlated with the long wavelength zeta long, okay, which is this guy over here in my example, okay? So this guy over here is now zeta long. And if there is a big 3-point function there, all that it means is that if you can think of it this way, in the initial conditions of this little box, the amplitude of initial fluctuations depends on where you are in this location. And it's just, if you have a large squeeze limit like that, it just varies with zeta. There's a part of this that varies proportional to zeta. This is not something you can mimic through the dynamics, because the dynamics only care about the tidal forces. So if this term is proportional to Laplacian of zeta, so if I make the long wavelength mode large, it's only the dynamics only cares about the curvature. Okay. However, if in the initial conditions I put that the amplitude is different in places in a way that if in the initial conditions, if zeta is something here, the amplitude is larger, then I can make this vary not with Laplacian of zeta, but with zeta. So there's this k-square of difference, and that's the k-square there, and so you can tell it apart. If you are an observer there, you will see changes, and you report back. So these are modes that are well outside the horizon of this observer, let's imagine, okay? And the observer measures the number density of galaxies, proper time, number density of galaxies, and send it back to me with some flashlight, okay? And I record this. Now the zeta mode is inside my horizon, so I know that, oh, this guy comes from a place where zeta is this way. The observer couldn't know. In this scenario, where if there's no squeeze limit there, what the different observer sees is identical, because it's only the Laplacian of zeta that's important. The Laplacian is very, very small because the mode is outside the horizon. So all of these observers report the same number density of galaxies, okay? However, in the cases where in the initial conditions there was some relation between the amplitude of fluctuations and zeta, they will report something different, because this, if you want, is a universe with some value of the sigma 8. This is a universe with some other value of the sigma 8, okay? It can depend, and if I put it in the initial conditions, it can depend directly on zeta, okay, which it cannot happen through the dynamics. So this k-square difference is very robust. It's just, it's not something that you can mock up by some complicated astrophysical stuff, okay? So I think it's a very good method, and it encodes in a 2-point function. It encodes information about this squeezed 3-point function. So it's good that in the 2-point function, because it's the 2-point function of objects, it cares about some 3-point function thing, and it's a very robust statement. Now, two final comments that I wanted to make. if rather than an observer, I was careful to say an observer there measures the same number of galaxies and so on. Even if there was no 3-point function like that in the initial conditions, but it was us counting the galaxies from here, there's a bunch of effects like gravitational redshifts and lensing that depend on the long wavelength mode that will make it that at a fixed redshift we are not comparing boxes at the same proper time, for example. The angles are not the same. So there will be effects that will make us see some modulation that depends only on zeta as opposed to Laplacian of zeta, which are things that are just projections, our own projections. But if we had a way of measuring directly densities and the time there, which in some examples we have, for example, the CMB happens at a specific time of recombination in proper time there. It doesn't care about us. Or if we measure relative densities of two population of galaxies, that ratio doesn't depend on the lensing, for example, because both, okay. So we have some handles on some of those things. But you might see some effects that are proportional to zeta if you don't take care of projections properly, okay? But if you are there, there should be no effect. And the last comment that I want to say is that if you had, I think Paula even mentioned that in the case of single field inflation, in the squeeze limit, the 3-point function is not, I said it was 0, but it really satisfies this consistency condition. So the amplitude is not 0, but in the way we have calculated following Juan, everybody calculates this 3-point function. This squeeze limit has to be exactly ns minus 1, okay? This consistency condition. But this consistency condition is just the way of expressing that there's no physical effect in comoving coordinates. I'm only getting, or one is only getting this ns minus 1 because he's computing not the power at a fixed physical scale, but a fixed comoving scale. And in the presence of the long wavelength mode, it scales the coordinates by e to the zeta long. And so in order to express that there's no effect in comoving coordinates, I need to shift things by the slope of the power spectrum so that there's no effect. And by no effect, I mean if you literally were an observer there and then reported back to us the number density of galaxies, in the case of inflation, it's not that you would see a very small effect proportional to ns minus 1 times zeta. Even if you were to measure it perfectly, you would see 0, because as long as you compare galaxies of a fixed physical mass, as opposed to a mass that depending on the place, okay? The reason why in the standard calculation you get a non-zero something in the squeeze limit, a non-zero value in the squeeze limit, is that you are comparing the 2-point function at two different scales in the two parts of this wave. Here and here, the same physical wave number corresponds to two different comoving wave numbers because of this scaling, or a fixed comoving wave number corresponds to different physical scales. So what is the same is that in inflation is the 2-point function at a fixed physical scale, okay? But because of your labeling of scales from place to place, you see in comoving coordinates a change which is just a fake, okay? So this ns minus 1 in the consistency relation is identical to 0. That's what 0 means in comoving coordinates, okay? So even if we were able to measure it perfectly, in the case of inflation, we should keep going and going and going with this squeeze limit and see nothing, okay? In fact, what we would see are terms that are proportional to the Laplacian of zeta, just because of the same reason. During inflation, the long wavelength mode can affect the short modes, but only by Laplacian things, okay? So a Laplacian thing I can generate, and that's how all of these 3-point functions that are generated in inflation, how they go to 0 in the squeeze limit, okay? But the constant part, this ns minus 1 that you just cannot get in inflation, and it's really 0. So anyway, so let me stop there, and that's it then.